The purpose of this video is to help us review calorimetry problems. And there's two important equations for these kinds of problems. Remember that these are kinds of problems that have two different substances that we are combining that will reach thermal equilibrium. And in that we have Q system equals the negative Q of the surroundings. And what that just means is that we have one thing that is releasing energy, and that is, or gaining energy, and that is exactly the same number but the opposite sign as what the surroundings is giving to or taking from this system. Because we know that Q equals mc delta T, we know that mc delta T of the system is equal to the negative mc delta T of the surroundings. And we will use that for all of these problems. You could solve this side for a Q, then make it negative and solve this side for another. But I'm going to show you how to do it in one step because I think that's a little bit easier. So let me clear this off real quick. Clear all of that. So we have our first problem, which says a calorimeter contains 100 grams of water at 22.4 degrees Celsius, 75.25 grams of aluminum at 99.3 degrees Celsius is added, and it cools to 32.9 degrees Celsius. What is the specific heat of aluminum? So I have a lot of information in here. One thing you can do is use a highlighter. I've got two different substances, and I want to keep those separate. So I've got aluminum, and I've also got water. So I'm going to highlight everything for aluminum in yellow. So this is 100 grams of water, so that's not for aluminum. But I do have 75.25 grams of aluminum. And I'm just going to highlight that too. It starts at 99.3 degrees Celsius, and then it cools to 32 degrees Celsius, and then we want to know what is the specific heat of the aluminum. So that's going to be our unknown. But then we also, let's make it blue. We have information about our water, which I'm going to make blue. Remember, we have 100 grams of water, and it starts at 22.4 degrees Celsius. The trick here is that we're always going to end up at thermal equilibrium. So this 32.9 degrees Celsius is the final temperature for both the water and aluminum. So I've got it in both blue and yellow. From here, I'm going to organize my table with my givens and my unknowns. So what I'm going to do is just list mc delta T for both my water and my aluminum. And I have all of that information, or most of it, already set. But remember, I'm eventually going to use Q equals negative Q. So the water versus the aluminum. So this is one side and this is the other side. So the mass of my aluminum, remember mass is in grams, so my grams of aluminum is 75.25 grams. My C for aluminum, or my specific heat capacity, is my unknown. So that's my question mark. And delta T, remember delta T is T final minus T initial. My T final is always going to be the one that has two colors. So it's 32.9 degrees Celsius minus my T initial, which is where I started for the aluminum. So it's 99.3 degrees Celsius. And it might look scary because this is going to end up being a negative number, but that's okay because we know that it is cooling down. So it's negative 66.4 degrees Celsius. This one's cooling down, so I know that when I go over to my water, the delta T has to be positive. One of them will always be cooling down while the other one is warming up. So now I need the mass of my water, which was 100 grams. Make that a little bit easier to see. It was 100 grams up here. C for water, it's not given here, but in general, you will be given that the specific heat capacity of water is 4.18 joules per gram degree Celsius. So 4.184 joules per gram degree Celsius. And then delta T, T final minus T initial. The final temperature, again, is the same on both sides, so 32.9 degrees Celsius, minus the T initial, which is where it started. The water started at 22.4 degrees. So the difference there, it's just 32.9 minus 22.4 is 10.5 degrees Celsius. From here, I just need to plug it in. So I still got this equal sign, and I'm going to bring across along that negative. And remember that Q is equal to MC delta T. So MC delta T. And I'm just going to plug all of the values I have in. So I've got 75.25 times my C, which is unknown, times negative 66.4 degrees Celsius, equals negative, my M on this side is 100 grams, C is 4.184 joules per gram degree Celsius, and my delta T is 10.5 degrees Celsius. Now this is where it gets a little bit funky, but that's okay. It's just basic algebra. So we're going to, let's use some green. I've got C over here and I want C by itself. So I'm going to divide both sides by what C is multiplied by. So 75.25 and negative 66.4. 75.25, negative 66.4. On this side, these guys all cancel out, and then I'm left with this mess over here. For me, I like to see that this negative and this negative will cancel out, so I don't have to put that in my calculator. So I know my answer is going to be positive when I end up. And since I'm going for a C, that makes total sense. My specific heat capacity will always be positive. So in my calculator, I'm going to multiply by anything that's on the top and divide by anything that's on the bottom. So I have 100 times 4.184 times 10.5 divided by 75.25 divided by 66.4. And I get C equals 0.879 joules per gram degree Celsius. And that's the final answer for this problem. I'll go through another one, but it's all exactly the same. So remember that what we're going to do is identify our givens and our unknowns, and then make a table and plug them all in. So let's start with this problem. It has a 13.5 gram sample of gold is heated, then placed in a calorimeter containing 60 grams of water. The temperature of the water increases from 19 to 20 degrees Celsius. The specific heat of gold is 0.130 joules per gram degree Celsius. What is the initial temperature of the gold metal sample? Remember that the specific heat of water is 4.184 joules per gram degree Celsius. So my two different substances, I've got gold. Hey, let's do that. Gold. And I've got water. If you'll notice, one of them is always water. So let's go through and highlight. I've got gold and yellow. So 13.5 grams, that's for gold. It's heated, placed in there. That's water. The water temperature changes. But the final temperature of this water is 20 degrees Celsius. That means that the final temperature of my gold is also 20 degrees Celsius because of thermal equilibrium. The specific heat of gold is this, okay? And then it wants to know what the initial temperature of the gold metal sample. So that's my unknown. And this is honestly probably one of the hardest problems we have. So It's okay. It's a little bit intimidating, but it's not that bad. Now I'm going to highlight any of my givens for my water. So my water was 60 grams. It was heated from 19 degrees Celsius to 20. And this is a little bit blue now. And then the specific heat of water is 4.184. So I'm just going to set up my table of values. So I've got MC delta T, and then MC delta T on this side as well. And that got a little sloppy, I'm sorry. So the mass of the gold, so gold's in yellow, the mass was 13.5 grams. The specific heat was 0.130 joules per gram degree Celsius. The delta T, so for gold, we don't actually know because we don't know the initial temperature, so I'm just going to make this one a question mark. The mass of the water was 60 grams. C for water is 4.184 joules per gram degree Celsius. And delta T, it went from 19 to 20. So T final is 20 degrees Celsius minus where it came from, 19 degrees Celsius equals a whole 1 degree Celsius. And then remember that we're just going to plug this in. So Q equals negative Q. You don't have to write that, but it might help you. So I'm just going to plug these in. Again, this is unnecessary writing, but if it helps you keep track of your thinking, you do that. And I'm just going to plug these in. So I've got negative 60, 4.184, and 1. And over here I have 13.5, 0.130, and delta T. That's my unknown. Now, in order to solve for the delta T, I've got to get rid of these guys. So these are, we're just going to divide both sides by 13.5 and 0.130, 13.5, 0.130. These on the left cancel out, so my delta T is left by itself. And I'm just going to put that in the calculator. So I see that I have one negative here, so that's going to come along for the ride. So my delta T is going to be negative. That makes sense because my delta T for the water was positive. So one of them will always have to be negative. So 60 times 4.184 times 1, and then divide by anything in the bottom. So I've got divided by 13.5 and divided by 0.13. So that my delta T equals negative 143 degrees Celsius. But remember, it wanted the initial temperature. And this is delta T. So delta T is equal to T final minus T initial. So if delta T, which is negative 143, equals T final, which we know is 20, minus T initial. So in order to get this to solve for T initial, I have to subtract 20 from both sides. So that goes to 0. And then this equals negative 163. But this is negative T initial. So these cancel out to be positive. So T initial equals 163 degrees Celsius. And that makes sense because if T initial was 163 and then it decreased by 143 degrees Celsius, then you'd end up at 20 degrees Celsius.